last few slides. And again, since today's experiment really is about a lot of it periodic trends and stuff like that, that would be good to finish it. We'll talk about the experiment afterwards here, which again is experiment 3 today. So we sort of finished up in lecture talking about basically all these sort of periodic trends. And we talked about several types of trends. We talked about ionization energy, which again is the energy required to remove an electron from the gas phase. It increases as you go up to the right and decreases as you go down and to the left. We also talked about electron affinity, which is the energy change when somebody gains an electron, increases as you kind of go up to the right, decreases as you go down to the left. We also talked about size of the atom. It gets smaller as you go up to the right and larger as you go down and to the left. And we also talked about electronegativity, which again is really the only topic from chapter 3 that you need to know about. And again, remember, electronegativity is the ability of an atom to bring electrons towards itself. Fluorine is the most electronegative, and it increases as you go up and to the right on the periodic table, with fluorine being the most electronegative, and decreases as you go down. Ultimately, what we saw with sort of all these sort of periodic trends is essentially what we sort of know about kind of metals and non-metals. So metals are essentially to the left of the periodic table. Non-metals are to the right of the periodic table. And especially when metals and non-metals get together, what we typically see in terms of electrons and so forth is that our metals are willing to really sort of part with their electrons. And that's why we typically will see metals become positively charged and are cations, while nonmetals, on the other hand, because really of all these sort of periodic trends, all those trends point to the direction that nonmetals really kind of like their electrons. They want to hang on to their electrons. And not only that, they probably want kind of like your electrons as well. So, they really hold on to their electrons, which is why we typically see nonmetals becoming negatively charged in anions and gaining electrons. So those trends really fit really nicely together. All those sort of trends, they all point in that sort of direction that there's not a lot of convincing for metals to give away electrons, and for nonmetals, they typically want to grab those electrons. That also would mean that in terms of reactivity, we would expect probably the most reactive nonmetal to be in the upper right of the periodic table, while the kind of most reactive metal would be more towards the bottom left. Again, those are sort of the extremes of all those sort of trends and either gaining or losing electrons. All right, so let's take a look at some of these sort of questions and sort of reason sort of through them here together. Which one is larger between our sodium and our chlorine? Again, if we were to sort of compare where these guys are on the periodic table, which, really for a lot of these type of questions, the general trends that we talked about is usually sufficient for you to make those sort of determinations, or a pretty reasonable guess. Again, here we see sodium further to the left on the periodic table than chlorine. They're both in the same period. And as we know, again, atomic size decreases as you go to the right and increases as you go left and down. So since they're sitting there in the same row, we would expect sodium to be sort of a larger atom. Remember, again, we talked a little bit about it as well, sort of a plus 11 versus like a plus 17 in terms of the protons that we see present in the nucleus. So remember, as we sort of build up that positive charge in the nucleus, it's going to bring everybody, even the furthest electrons, kind of in closer to begin with, because of that kind of greater positive charge that we see in the nucleus. Which one is a larger atom between lithium? I'll spit that out. Maybe lithium and cesium. Again, just the location wise on the periodic table, they are hanging out in the same group. And again, lithium is higher in the group than cesium. So for the same reason here, we would expect the larger one to be cesium. And remember, size increases as we go down a group. Again, same sort of idea. in the sense of this guy really has only got 3 electrons total. Cesium is like 55 electrons. So just the presence of those 55 electrons is going to make a much larger, obviously, electron cloud than like the 3 electrons that are hanging out here. Just the room of how much more that's got going on in terms of electrons and stuff like that. So again, we would see sort of a larger size and expect a larger size overall for our cesium versus our lithium. So here we got a couple of different questions, which is which one is larger, the hydrogen 1s orbital or the lithium 1s orbital? So let's start with that question. Which one is larger? Is it the hydrogen 1s orbital, or is it the lithium? And the answer is it's going to be the hydrogen 1s orbital. And that is because hydrogen really only has +1 charge, right, in terms of the sort of positive charge. So again, it's not going to pull that 1s orbital as close or as big as our lithium, which has a couple of electrons sort of occupying there. So we do have hydrogen as having a larger 1s orbital. But which one would be lower in energy? That has to do with sort of that positive charge, this guy being our hydrogen, this guy being our lithium here, right? Lithium, that's what we're looking at. And again, if we have sort of our 1s orbital, the electron that's in there, right, has got like an electron in there. This guy's got a couple of electrons sort of in there. And this guy is going to feel a pull, but this is going to be that +3 pull that's going to happen. Again, going to bring everybody in much closer, and it means that 1s orbital would be brought closer in to the nucleus and thus being lower in energy. Any questions on those two there? And then sort of put these guys in order of ionization energy. So we're looking at sulfur, oxygen, and fluorine. So if we look at the periodic table, we have sulfur, oxygen in the same group. To the right is fluorine. And in terms of ionization energy, right, we are increasing as we go to the right. So we definitely know that fluorine should be more ionization energy than oxygen. We also know it decreases as we go down, which means that sulfur should be less in terms of ionization energy than oxygen. So in increasing ionization order, that would give us our sulfur, oxygen, and fluorine basically coming up, increasing ionization energy, and then over increasing ionization energy. In terms of atomic size, right, it's sort of opposite there. So atomic size gets smaller as we go this way and larger as we go this way. So that means that going to the right, fluorine should be the smallest, and then obviously going backwards there. So just redraw that like that. This guy here should be the smallest, heading in this direction, and then be larger, and then heading down should be larger. So fluorine, oxygen, and sulfur in terms of the increasing in size. Any questions on any of that there? So we talked a little bit about periodic table, some electrons. So in general, the number and type of valence electrons are primarily determine sort of the atom's chemistry, as we'll talk about obviously in the next chapter, which is about bonding, and we sort of alluded to here in this chapter as well. It's really those valence electrons, because they're the furthest away from the nucleus, and in relatively speaking, compared to the core electrons, not held as tightly, they're really the ones that are involved in all kinds of bonding and every aspect of bonding, and really sort of chemical reactions as well. Again, just visually, just simplifying it, the electrons on the outside. So obviously when two atoms come together, it's those outermost electrons that are first going to interact with each other, which is going to cause obviously all kinds of bonding to occur. Electron configuration can be determined from the organization on the periodic table. So again, we talked about that, there's the S block, the P block, the D block, and the F block. And I think we did a couple where you could just read off the electron configuration for the periodic table. Again, with that cautionary note, as we talked about there, that you want to make sure that you remember that after the 4s, it is the 3d. And again, that D is 1 behind the period number. And if you get into the Fs, which are the bottom 2 rows, those guys are 2 behind the period number if you were to sort of count those guys off. We obviously talked about special names in terms of the periodic table, alkali metals, alkaline earth metals, halogens, and noble gases. Obviously, where our transition metals are lanthanides and actinides. Since we've been talking a little bit about charges and things with charges, and it'd be a good thing to talk about here, kind of leading into our discussion about bonding in the next chapter tomorrow. I mentioned it a second ago, I think, or a little bit ago, that, things don't really have charges, when they are by themselves. So sometimes there's a misconception from students that, when they think about, oh, I know sodium always has a +1 charge. That's sort of what was beat into my head at some point, probably in a chemistry class. But, so if I have sodium metal by itself, it obviously has a charge, and that's incorrect. So pretty much if you take any element, from the periodic table, and it's really not combined with any other element, just by itself, these things do not have charges. So again, things really only get charges really in ionic compounds, and really when we put together a metal and a non-metal. And because of all those periodic properties we've been talking about, again, the metal in that situation is going to give away its electrons. And that's really the process where that guy becomes positively charged. And the non-metal, because of all its properties of I want those electrons, are going to pick up those electrons and become negatively charged. And it's at that point, we get something that does have a charge. So if we think about sodium chloride, and we do write the formula obviously like this, that has no charge, it is made up of 2 things that really do have charges. And these guys originate from really sodium metal that has no charge, and chlorine gas, which obviously has no charge as well. So again, these are sort of the element forms that as they start, they really have no charge. It's not until they kind of come together and the sodium goes, here, take my electrons, chlorine gains the electrons, then we really form something like sodium chloride that guy has both a positive and negatively charged sort of aspect. So again, it's a very common thing that people always think, because we do nomenclature a lot and stuff like that. So we think, well, if I'm dealing with sodium, no matter what the situation, it's got to have the +1 charge, which is correct when it does gain a charge. But again, if it's by itself, it really doesn't have a charge. Any questions on that? So speaking about charges, there are certain things that when they actually do gain charges, and really an ionic sort of compound, there are certain things that are elements that will have what are sometimes referred to as sort of fixed charges. So these are guys that no matter what the situation is, when they actually do go to form something that has a charge, they always will form really the same charge. And now that we know about sort of group numbers and all that, it's a good way to sort of figure out the charges. So everybody in group 1, no matter what the situation, will always form a +1 charge. So that's why we see sodium, which is group 1, has a +1 charge. If we're talking about something like lithium, it will be a +1 charge. Potassium will be a +1 charge. Again, when it does gain a charge, that is always the charge that you will have. You'll never have anything like sodium with a +2 charge. And it really does go back to what we were talking about a little bit earlier today. If you remember, I think it was on that chart, but I think to remove sodium, which has 1 valence electron, you could remove that one. I think it was like 400 and some odd kilojoules of energy, ionization energy. To remove the second electron, which then would move you into those core electrons like we were talking about, it jumped up to like almost 5,000, I think, in terms of energy required to remove that electron, which really doesn't happen under those cases, because you have now dealt into sort of the core electrons at that point. And that's why sodium will always be +1. You'll never see it with a +2 or +3, because that would mean that you had to rip out those core electrons, which under really normal circumstances will never happen. And that's why we say sodium has a fixed charge. Same thing with lithium. Again, when you get to like the second electron with lithium or potassium, you're now moving into those core electrons. So as we saw with the ionization energy, you see a tremendously giant jump in terms of the energy required to remove those electrons, and they typically just doesn't happen. And that's why we say everybody in group 1 pretty much has a +1 charge. Everybody in group 2, surprisingly enough, will have a +2 charge pretty much. So that's why we look at something like magnesium has a +2 charge. That was also, if you remember, on that ionization energy sort of slides that we were looking at, and we saw there was like the first ionization energy, I don't know, I think it was 700 maybe or something like that. Second one went to like 1400. And then when you got to the third one, because magnesium has 2 valence electrons, when you get to that third electron, you're now again into the core electrons. And it went up to something like 8,000 or something kilojoules to try to remove that, which again just does not happen at that point. So you can see sort of the relationship between these fixed charges and the number of valence electrons that these guys have. The number of valence electrons sort of helps us understand, you know, which ones are going to be easily lost because of all those periodic trends we've been talking about. But again, once we get those guys lost, and every time we do lose an electron, as we talked about, the overall size of the guy just starts to shrink, right? It gets smaller and smaller, making those outer electrons that may have started here, once you lose that first one, now it's maybe closer in, going to be held a lot tighter, closer to that positively charged nucleus, and can take more energy to remove it. In terms of transition metals, we typically do skip these guys, and we go to group 3, where everybody pretty much makes a +3 charge. And when I say by everybody, pretty much we're talking about aluminum here. It's going to be a +3 charge. Gallium is going to be +3, can have other charges. Boron, again, is our sort of metalloid or non-metals, so probably not going to become positively charged. As we go down this way, these guys have a little bit more variety in terms of the charges. So usually when we talk about group 3, usually it's reserved for usually aluminum will be +3. Again, sometimes gallium will be +3 as well, but aluminum is usually what we're talking about. As I just mentioned, again, this is sort of where we have our sort of staircase, right? That's sort of coming down. And what ends up happening is we do skip group 4 and go into group 5 in our non-metal region up here above this sort of staircase. This is where these guys would be gaining electrons. And it sort of goes backwards. We kind of go +1, +2, +3, which is what we would expect to happen with metals. As they lose electrons, they become more positive because they have more protons than electrons. But now in non-metals, based on all those periodic trends, as we've been talking about, those are guys that are going to accept electrons. So now if they accept electrons or gain electrons, they now have more electrons than protons, and they become negatively charged. So typically group 5 is -3, group 2 is -2, and group 7 is -1. So we kind of go +1, +2, skip the middle here, +3 at aluminum. We skip 4 because really group 4 is a combination of like everything. At the very top, you got non-metals, you have some metalloids happening, you got some actual metals that are below it here. So, you know, group 4, you know, you got things like tin and lead down here, which are, you know, essentially, actually, I kind of missed it there. I went a little too far down. I think that's actually tin, and this is lead here. But you got things like tin and lead, which actually are metals. So they're more positively charged. You got things that are more non-metals, which, you know, more negatively charged. So there's no real good pattern that sort of happens in group 4. And it's important to also note that when we are talking about -3, -2, and -1, we're talking above the staircase in our non-metal region. Again, because if you go to the staircase or below the staircase, you're dealing with metalloids and metals. So again, they would not be negative in that particular case, especially the metals, obviously, as well. Now, in terms of our transition metals typically can make a variety of charges. So they can have a variable type charges sort of in our transition metal region. So sort of our transition metal region here can have a variable type of charge. And even outside of that region, places like in here where we have, kind of antimony, I think is somewhere in this ballpark, and bismuth and these sort of guys. These guys as well over here, which again are below the staircase, and our metals have a variable type of charge. And what I mean by that is, again, if we look at something like iron here, iron in certain cases can be iron 2, it can be iron 3. So depending on sort of the circumstance, it's possible to get iron with a couple of different charges. Something like copper, for example, same thing. Copper in certain cases can be copper 1, it can be copper 2. So you have this sort of variety or variable type of charges that typically occur in our transition metal regions when they do gain charges, and also slightly outside of the transition metal regions, just to the right, places where we have lead, which is Pb, tin, which is Sn, antimony, bismuth. These guys have a variety of sort of charges. The only three sort of exceptions that we commonly come across within the transition metal region that are sort of fixed charges are really these three guys here. It is zinc, cadmium, and then if you hang a left, make kind of like this backwards L, to silver. So these three transition metals, even though they are transition metals, they actually have fixed charges. So these guys have fixed charges, kind of like group 1, group 2, and group 3. They always will form these charges, and the charges that they have is silver is always +1, zinc and cadmium are +2. So zinc and cadmium will always be +2, silver will always be +1, and that sort of backwards L here in the transition metal region are really the only sort of transition metals that have these sort of fixed charges. Pretty much everybody else, just like iron and copper, nickel, for example, could be +4, +2. Mn could be all kinds of charges. +4, +2 are common ones. So they have these sort of variable charges. Any questions on any of that there? Also, why we have this here, again, in terms of charges, hydrogen, as we talked about a little bit earlier, kind of special in the sense, again, occasionally was found on both sides of the periodic table. A reminder that hydrogen is a non-metal, and hydrogen kind of the only ones that could kind of go both ways, in the sense of hydrogen can be positively charged in some cases, and it can actually be negatively charged in other cases. So hydrogen can gain a negative charge typically when it kind of goes with a metal. So if hydrogen sort of follows a metal, hydrogen sort of acts as a non-metal like it is, and it will become negatively charged. So this is really +1 and -1. But hydrogen that typically comes in front kind of acts like a metal in a sense and becomes +1, and the non-metal becomes -1. So hydrogen kind of weird in some cases in terms of how it behaves. It is really a non-metal, but it can behave almost like a positively charged cation in a lot of cases. And we'll see some of those cases as we go through some different chapters. Any questions on the periodic table, sort of the normal charges that things make? Again, that'll be very helpful, obviously, for bonding and stuff like that we're going to be talking about in the next chapter. Okay. So just to finish up here, again, we talked about where everything's located, I think, and our alkali metals, again, are lithium, sodium, rubidium, cesium, most chemically reactive of the metals. Yeah, if you put like sodium in water, it's very, very reactive. Potassium water, very, very reactive. Reactive, like it will catch on fire, actually, as it's kind of doing those things. And again, because it produces hydrogen gas, so it sort of ignites and stuff like that. So a couple finishing thoughts here again about going down the group. All those trends that we sort of talked about, or some of the trends that we talked about, ionization energy does decrease, atomic radius increases because of the increase in a number of electrons that are present at that point, and density actually increases, melting and boiling points kind of decrease a little bit as you go down. Any questions on any of that stuff there? That should wrap chapter 2. And just so we're clear, this also wraps up the material that's going to be on exam 1. And exam 1 is 1 week from today. I'm not sure if that's July yet or not, but probably not 28th, maybe it looks like, maybe 6/28. So that's next Monday. Again, it will cover all of chapter 1, all of chapter 2, and the only thing from chapter 3 that you need to know is electronegativity. And what you need to know is what we talked about today with it is just the general trend. We will talk in greater detail in chapter 3 more about electronegativity, but for this first exam and stuff like that, really you need to know that electronegativity is the ability of an atom to bring electrons towards itself, and that the general trend again is it increases as you go up and to the right, fluorine being the most electronegative, and decreases as you go to the left and down. Any questions on any of that there?